So let's pick up where we left off last time. We are talking about these substitution reactions that our aromatic compounds undergo here. And so there were 6 different ones of these substitution reactions that we learned. Substitution, right? So we're putting different things around this benzene ring, okay? So these 6 reactions, we also sort of noted that we had 2 special ones because they would transform one of those substituents into something else. Okay, so there were these 2 reduction reactions. It's kind of annoying that they're different reagent lists, but let's just note that both of them have this same zinc metal in there, and both of them do the same thing insofar as they're replacing these oxygens with hydrogens. Okay, so just kind of we can lump those together a little bit in our brain in terms of what they're doing to these substituents around the ring. So then we talked about how our substituents would fall into 2 different categories. Electron donating substituents, which would then lead to these ortho-para directing groups. So they'll place any incoming substituent in a specific place. And the other category were these electron withdrawing groups. All right, and so they'll take any incoming substituent and put it in the meta position. Okay, so we're going to pick up right there, and we're going to look at this master list of our substituents here. I'm going to make it smaller so we don't get too scared yet. Let's go one by one here. All right. So our first category is strong activators. By activators, we mean electron donating groups. Why would we call them activators, these electron donating groups? Exactly, because these electron donating groups, they're adding electrons to the ring, and that makes benzene even more nucleophilic. So absolutely, okay? And remember we said that these are ortho-para directing groups. All right, so let's take a look at a few of these and see if we can't figure out what they all have in common here. All right, in each one of these, we have that lone pair located in the benzylic position, right next door to that ring. So all of these strong activators, we can say they have a benzylic lone pair. All right, so then we got this next category. We're going to classify these as moderate activators. All right. They are still going to be electron donating groups, but they're not quite as good at donating as the ones above, as our strong activators. So electron donating still, but not as good. Because they are electron donators, they are still ortho-para directing groups. Okay, so let's take a look at these and see what they have in common. All right, what do these all have in common here? Do we still have allylic lone pairs? Right? Sorry, not allylic. Benzylic lone pairs. Right? We still have these lone pairs located right next door to the ring. So then what differentiates these from the ones above? That carbonyl group on the other side, right? And remember, these carbonyl groups are electron withdrawing groups. So they kind of pull those lone pairs towards it a little bit making it so they can't really go towards the ring quite as well. We can explain this in terms of resonance by looking at this. Yes, we can draw one resonance structure where this lone pair comes down and joins that ring. Boom, boom. That's that classic electron donating behavior. But we can also draw a resonance structure the other direction, where that lone pair is now being removed from that benzylic position. All right, so these are why they're not quite as good at donating electrons, because those electrons can bounce in either direction. Right? Effectively, this carbonyl group here is pulling some of that electron density towards itself. So there's not as much left over for the ring. Okay, so we can say our common feature here, benzylic lone pair with electron withdrawing group on the other side. All right, I'm going to skip over one category real quick and come down here. These are now weak deactivators. Okay, and this category is a little bit weird because this particular category is still an ortho-para-directing group. All right, so what do all these have in common? They're all halogens, right? So halogens both have an allylic, not allylic, benzylic lone pair, so they can donate that pair of electrons to the ring, but they also all are very electronegative, and so they withdraw electron density from the ring through induction. So there's kind of this push-pull going on where, yes, they still have a lone pair to lend to the ring, but at the same time, they're sucking electron density out of the ring by virtue of being electronegative. So that's why they're considered to be deactivators, meaning that they react even slower than benzene all by itself, but they're still ortho-para-directing. They still have that lone pair. All right, so before we move on and I complicate things, let's just note every single one of these ortho-para-directors here have this same common feature of having a benzylic lone pair. So if you see a benzylic lone pair, you automatically think ortho-para-directing. We got to think a little bit harder to think whether it's strong, moderate, or weak. All right, but all of them have that same feature. Okay, and so let's just note these are our halogens. They have a benzylic lone pair. But withdraw electrons through induction. Which is what we call it because they're electronegative. All right, so it's through their electronegativity that this induction effect is observed. Okay, now the last category here, also ortho-para-directing, but they're going to buck this trend of what we saw with all the other ortho-para-directors. We consider them to be weak activators. And what do all these groups have in common? Yeah, carbons and hydrogens, right? These would be just all alkyl chains. Notice there's no lone pair. That's what I mean by they're bucking this trend. There's no benzylic lone pair anymore. But alkyl groups are also considered to be ortho-para-directors, and they are weak activators. All right, and this sort of activating power, albeit a weak activating power, comes from what's called hyperconjugation which is the same effect that we see that stabilizes a carbocation, which is why a tertiary carbocation is more stable than a secondary, is more stable than a primary, right? The presence of those carbon-hydrogen groups is what activates this benzene ring here. Okay, so now we're going to get into our electron withdrawing groups. All right, our moderate deactivators, which are now meta-directing group because they withdraw electrons. Let's see what all these have in common. What is bound to that ring? A carbonyl carbon. Right? This is the electron. This is an electron withdrawing group. We talked about this and drew out these resonance structures when we were looking at Diels-Alder reactions. All right, but here we have carbonyl carbons. And again, these are now electron withdrawing groups. Okay, and just to kind of illustrate this using resonance structures here, this carbonyl carbon is able to take electrons out of that ring because it can bounce that pi bond onto that oxygen, right? So this is this electron withdrawing effect of a carbonyl group. All right, and there's one more to add to this list here, and it's going to be important because we actually know how to make this for one of our electrophilic addition reactions. Oh, well, there's just another carbonyl. Is this sulfonic acid group here. All right, remember we know how to put this SO3H group on the benzene ring, and now we know that it is considered to be a moderate deactivator, which is meta-directing. So carbonyl carbons and our sulfonic acid group. Maybe sulfonous, I don't know. Good enough. All right, and then the last three. These are the big, strong meta-directing groups. Okay, first one, coolest name of all of them, that nitro group we learned about. Again, we learned how to put this on the ring, so it's going to be pretty important to note. Strong meta-directing group. Okay. Any sort of a fully maxed out nitrogen such that it has a positive formal charge. So R can either be carbons and hydrogens or just hydrogens here, right? But if you get it to where you have, so for example, if we take aniline and put it in acidic conditions, we would get this strong meta-directing group. Okay, and then the last one here is if you have a carbon that's fully substituted with halogens. Okay, and this one's also sort of going to be important to note. This last category, there's only 3 of them, but we just got to know them, right? There's not really that same common feature that we can spy among them like we could with our lone pairs. All right, but yes, here's your grandmaster list of substituents and their behavior with regard to directing incoming substituents. If you would like to take a picture, go for it. All right, but yes, importantly also make sure that you can spy these common features, right? Because we're not going to have the master list on the exam. Cool, all right, so we talked about why this ortho-para versus meta-directing was important for when we start doing reactions with these compounds, right? We would get a different product depending on the order in which we conduct these reactions. So we got these 6 reactions, but it turns out in which the order in which we do them will dictate what our product is, right? So that's why we're going to have to pay attention to this ortho-para versus meta business. There's another set of reactions that let's just make note of because they're pretty important in this chapter. All right, and these are our methods for converting orthopara into meta-directing groups and vice versa. All right, so there are a few reactions that we know that they're not going to put something new on the ring, they're going to change what's already on the ring. And in fact, they would change an orthopara into a meta-director or vice versa. All right, so let me just grab a benzene so I don't have to draw it over and over again. Okay, so the first two are those two that we talked about last class. If we take a nitro group, we can use that zinc, HCl, followed by NaOH, and that would convert that nitro group, fully reduce it into aniline. All right, this nitro group is what? Orthopara or meta-directing? Yeah, this one's in fact one of our 3 strong meta-directing groups. And what about aniline with its benzylic lone pair? That would be orthopara, and in fact this is a strong orthopara director. All right, so if we do this conversion here, we'll convert one of our strong meta-directors into one of our strong orthopara directors. Okay, the next one. We learned how to do these Diels-Alder reactions and put these acyl groups on. And then we learned that you can pop these off, again, reducing that using zinc. But this time, for whatever reason, the list is a little different. Zinc, HCl, and heat. And that will fully reduce that carbonyl carbon to just an alkyl carbon. Chop off that carbonyl oxygen altogether. Whoops. All right, that not Diels-Alder, Friedel-Crafts product with that carbonyl carbon located right next door to the ring. That's going to be a meta-director, and in fact, these were moderate meta-directors. And then we chop it off and we just have an alkyl group. Remember, alkyl groups were kind of weird, but they were orthopara directors, and they were weak orthopara directors. All right, we got 2 more to add to this list, but they're reactions that we already learned last chapter. All right, the first of which was if we take an alkyl group, let's just call it R. We can make note that R can't be quaternary. But it didn't really matter how long that chain was. If we take this and we hit it with that chromium containing reagent, you see chromium and you think what? Oxidation. And that benzylic position gets fully oxidized into benzoic acid. Okay, we said these alkyl groups were weak orthopara directors. What about benzoic acid? Yeah, so we got that carbonyl carbon bound to the ring. So this would be moderate meta-director. Okay. And then the last one is if we took this methylbenzene here, which we really don't call methylbenzene, it's got a special name. What is that? Toluene. All right. And again, this one is weak ortho para. We took that toluene and we treated it with a huge excess of NBS. We would brominate that benzylic position, right? But if we had a huge excess of NBS, we would get a fully brominated methyl group. So now all three of these bonds are going to be bromines. All right, and this was important because if we looked at that master list again, one of these strong meta-directors here was if a carbon was fully substituted with halogens, and of course a halogen is Br, right? So we know how to make this guy as well, this strong meta-directing group here. Cool. All right, so we got these reactions. These, first of all, where's my cheat sheet? There we go. We first learned about these 6 electrophilic aromatic substitution reactions, right? Where we can stick something on a ring. And then we learned that if we were to order these reactions in a certain way, certain groups like bromine would direct to an orthopara position. Other groups, like the nitro group, would direct to a meta position. All right, so we have our groups. They each have different behaviors. Okay, and then we ranked them in terms of these strong and weak, right? So then if we looked at our master list here of possible substituents, which I really should make a copy of because it gets lost. There we go. All right, we rank them as strong, moderate, and weak. So why do we do that? All right, we have the orthopara directing. Now we added this next layer of complication, this strong, moderate, weak. Okay, so let's take a look at a particular reaction. I'm going to take my benzene ring. And the first thing that I'm going to do is this reaction right here. I want you to tell me what the product of that would be. And then we're going to take that product and we're going to perform this reaction right here. All right, so tell me what the product of these first 2 steps would be. right, so step one, it's going to put a nitro group on that ring. Step two is going to put a bromine on that ring. But in what position? Right, so this one, we got to look at what's already on the ring. The bromine doesn't get to decide. It's what's already on the ring that gets to decide. And this is a meta director, so it's going to be directed to that meta position. Cool. All right, so now let's say that we take this and we're going to do yet another reaction with it, a third substitution reaction here. Okay, this time we'll add a chlorine on there. All right, so the question is, where does that chlorine go? In which one of these positions? Okay, and we said that this nitro group was a meta director. So the nitro group is going to try to direct this incoming substituent to the position that is meta to the nitro group. My halogen, on the other hand, is what? Ortho-para-directing. So it wants to direct the incoming chlorine to the positions that are ortho or para to the bromine. So we got some conflict here. The nitro wants it to go one way, the bromine wants it to go another way. So which one's going to win here? That's when the strong, moderate, weak business comes into play, right? This nitro group we said was a strong meta director. And bromine we said was a weak ortho-para director. So who do we think is going to win? The strong one, absolutely. The strong will win. Okay, so our final product, we'll have our bromine and our chlorine meta to that nitro group. All right, and again, the whole principle here is that stronger will win. So what if one was strong and one was moderate, who would win? The strong. And what if one was moderate and one was weak, who would win? The moderate, right? So whichever one is stronger will win. Okay, cool. So obviously one of the big challenges of this particular chapter is not so much those 6 individual reactions that we learned, or I guess a total of 10 if we're going to count those 4 that convert groups as well. But the fact that we mix and match that crap, right? That's where the real sort of complication comes into play here, all right? So 2 different types of problems that we can throw at you here. One is to say, I'm going to give you these steps, and you need to follow them in the correct order to give me the correct product. All right, so that's what we're going to practice first here. Here's a bunch of steps, a bunch of reactions. We're going to do back to back to back. You need to follow these steps in order to give me the correct product. right, so let's go through this. For this first reaction here, what am I going to be putting on the ring? Reaction 1. Chlorine. So after that first reaction, I'll have chlorobenzene. And then I'm going to follow that up with a second reaction here. What is this reaction? What functional group is that going to put on the ring? A nitro group. Okay. And now I got to figure out where that nitro group is going to go. Our halogens are weak, what? Ortho-para. Okay? And so remember, that means that we're going to have to draw both the ortho and the para product. So I'm going to draw one product with the nitro group in the ortho position and another product with the nitro group in the para position. Okay? Now the last thing that I could ask you about this is which one of these is our major product? The ortho or the para? Why the ortho? Because there's 2 orthos and only 1 para, right? And the other thing factoring into my decision here is that chlorine is just a monatomic group, a small group. It's not a big bulky group, like if it had a bunch of carbons coming off of it, all right? So yes, we would get just about a 66 to 33 or 2-to-1 distribution of these 2 products here. So yeah, this ortho would be my major. Okay, now we got a bunch of stuff going on here. So let's follow this one by one. That first reaction is going to do what? Make me which compound? Absolutely, we got a special name for it, right? So this is one of those Friedel-Crafts reactions. I'm again using this same catalyst. We see AlCl3 a lot. And it's actually always doing the same thing, which is removing that chlorine, and the other thing goes on there, right? So that's why this methyl group is what comes onto my ring here. So that's reaction 1. All right. Now I'm going to take this and hit it with this reagent which contains chromium. And again, when we see chromium, we're going to think oxidation. So now we'll oxidize toluene to one of those carboxylic acid groups. Okay, importantly, this chromium didn't put anything new on the ring. It transformed that toluene into a carboxylic acid group, into benzoic acid specifically. All right, so now I'm going to do fuming H2SO4. What does that do for me? That's that SO3H group. Okay, so I'm adding something new to the ring here. So let's take a second and think, where should that go? All right, we have to look at our carboxylic acid and determine whether it is orthopara or meta-directing. All right, this has one of these super common features of meta-directing groups, which is that carbonyl carbon. So this is a meta-directing group. So my sulfonic acid groups will go here. All right, and then my last step is going to add what to the ring? Bromine. Okay, I got to figure out where that bromine is going to go. So I got to look here. We said that this was a meta-directing group. So it wants to direct to the carbon that is meta to it. Okay, what about our sulfonic acid group? Orthopara or meta-directing? So this is also a meta-director. It's actually moderate meta. It's a weird one. It's the outlier in the moderate meta that is not a carbonyl carbon. All right, so this is also a meta-director. It wants to direct to the position that is meta to it. Well, it turns out that that's the same carbon. So in this case, there's no conflict. We don't have to worry about who's stronger and weaker. They're both in agreement that it's going to go to that carbon there. Okay, so my final product here will have all three of these groups spaced out evenly. Oops, not purple. Okay, so if I do 4 of these reactions back to back here, this will be my unique product. Okay, so much more complicated of a synthesis problem would be if instead of giving you the steps here, I said, here's my benzene ring, tell me how to make the following product. Okay, that's a much more complicated problem. It really requires a good understanding of these 6 reactions here. If you can't tell me what fuming H2SO4 can do, you're going to be in big trouble, right? So these are really important reactions to flashcard here and to practice. And these are great flashcard reactions because you can just kind of mix them up and draw 2 of them and put them down and say, all right, what's my product going to be, right? Just mix and match those reactions. That's the name of the game here. All right, so we're going to practice those types of problems, but there's one more thing we got to learn. And that is what's called not an electrophilic aromatic substitution reaction, but a nucleophilic aromatic substitution reaction. Oops. All right, in these ones, benzene is not playing the role of a nucleophile. Now we're going to see benzene is the electrophile. So benzene's the one getting attacked here in these reactions. All right. But these actually are a much more limited subset of reactions. There are some pretty strict conditions that we have to have for a molecule to actually even undergo one of these nucleophilic aromatic substitution reactions. Because we know our benzene ring with all those pi electrons is not a good electrophile. It's not an electron poor species. It's got a ton of electrons floating around in that ring, right? So there's some strict conditions here that we have for a molecule that will actually undergo. The first one is that it has to have a strong electron withdrawing group, which remember are our meta-directors. So one of those 3 strong meta-directors, that's what has to be on the ring. So a naked benzene ring all by itself will not undergo these reactions. It has to have one of those strong meta-director groups, like a nitro group. Okay? Not only that, the ring also has to have a good leaving group, which would be a halogen. And not only does it also have to have a halogen on there, that halogen has to be in a specific position. It has to be in the ortho or para position. So not only do I need a strong electron withdrawing group, I also need a good leaving group in either the ortho or the para position. All right, so your reactant has to meet these 2 criteria here. And then we could react it with some nucleophile. It's got to be a strong nucleophile. All right, but what will happen is that nucleophile will displace that nitro group. Nope, I lied. It would displace the leaving group. obviously. That's the one that leaves. All right, and I know y'all have done nothing but stop thinking about nucleophiles since we last learned about them, but maybe let's cover what makes a good nucleophile here, all right? So what can we use in these reactions? What are our good nucleophiles? All right, so first of all, remember nucleophile, electron rich or electron poor? Electron rich, and that's what we're going to see over and over again here. So for example, if we have any sort of an oxygen with a formal charge of -1, this is going to be a great nucleophile here, right? Whether it's something like a hydroxide ion or a deprotonated alcohol, an alkoxide ion, or even a deprotonated carboxylic acid group, a carboxylate. All right, all of these are oxygens with a net negative charge. These are going to be some good nucleophiles here. We could also have a nitrogen with that net negative charge. So that could be an amide ion or a deprotonated amine. Or a deprotonated amide. Any one of these, right, where we see a nitrogen with a net negative charge, these would be good nucleophiles. All right, and then the last one would be carbanions. Those are a little bit more rare. They're not very stable at all. Okay, one that we do see kind of a lot is, so let's make note here, are one of those nitrile groups. So the carbon that's triple bonded to a nitrogen, right? Or I guess more specifically a cyanide ion is the name of this thing. This would be a good nucleophile as well. And charge-wise, what do these all have in common? They got that net negative charge, right? So that means a good nucleophile. The one kind of oddball is sulfur. Sulfur is a great nucleophile regardless of whether it's protonated or deprotonated. So regardless of whether it's net neutral or net negative. Both of these are just as good. Right? We can also have a thiol group or a deprotonated thiol group. All right, any of these would be great. So let's just note that if our ring does have any of these on here, like if we had made, specifically if we had an OH group on there, we would have had to have used one of these nucleophilic aromatic substitution reactions. Or if we have a thiol group on there, or a sulfur linkage on there, right? Cyanide ion, all of these would have to go through these nucleophilic aromatic substitution reactions. We don't know how to make them otherwise, all right? The one exception is aniline. We do know how to turn a nitro group into aniline, so that doesn't necessarily signal. But if I see a phenol on that ring, if I see an OH group on that ring, I know it has to have gone through one of these reactions. That's the only way we know how to do it. All right. So before we move on, let's just practice this. All right. I'm going to start out, let's, for the sake of practice, put it over here. And now I'm going to react this thing with NaOH. All right, so first of all, what did I tell you? Every time you see sodium, what should you do? It's more confusing than it's worth, all right? Sodium is absolutely never going to be, the sodium ion rather, is absolutely never going to participate in any organic reaction ever. Right? Same with a potassium ion. These things are just going to float around in solution as counterions. So in my mind's eye, when I see something like NaOH, I immediately erase the Na and give it a minus sign. I know that that anion right there is going to be the one that's involved in my reaction, not the sodium. Okay? And so what's going to happen is the nucleophile, my hydroxide ion, is going to replace that good leaving group, that chlorine. Okay? So this is our last category of reaction for this chapter, these nucleophilic aromatic substitution reactions. Now benzene is the thing getting attacked by a nucleophile here. All right, but we got some pretty strict conditions on what will undergo these reactions here. You have to have a strong electron withdrawing group, and you have to have a good leaving group, and that leaving group has to be in the ortho-para position. These are the only ones that you can react with those nucleophiles, all right? And remember, by nucleophiles, I mean these things that have oxygen, nitrogen, or carbon with that negative charge, okay, or the one oddball, the sulfurs. All right. So now we're going to work on worst case scenario here, where I'm going to give you a target molecule, and you're going to tell me how to make it. Right, so I want to convert benzene into this thing right here. Okay, and you need to tell me the steps how to do it. All right, so I'm going to put down a few of these here. Give you some time to work on it yourself, and then we'll go over it together. go through this. So, I'm going to look at my product here. And I'm going to look at each one of these groups, and I'm going to think about how I can make that. All right? How can I put a chlorine on the ring? So, I got to know my reactions here. So this would be my Cl2 with aluminum chloride or iron chloride, that's fine. Okay. And what about for those sulfonic acid groups? Whoa. That's that fuming H2SO4. Okay, cool. So I know which two reactions I need to use. All right. But now I got to think about the order in which I'm going to perform these two reactions. In my product, these two groups are sitting meta from one another. If I look at my groups, the chloro is an ortho para directing, but the sulfonic acid group is a meta director. So I want to make sure to do that meta directing reaction first. So first, fuming H2SO4. Then I'll do that chlorination reaction. Okay. So now I have this methyl aniline here. I got to think of how we can make each one of these groups. An aniline, I don't know how to do in just a one step here, right? What I do know how to do is I can first do a nitro group, and then I can reduce that with the zinc, HCl, and AOH, right? We got to do that two-step there. There's no one-step way to put an aniline on there. We haven't stepped that. Put a nitro group and reduce it. For my methyl group, I do have a way to do it, right? I can use that Friedel-Crafts reaction, methyl chloride, with aluminum chloride. All right, we know how to stick alkyl groups on the ring. If I look at my product here, these two groups are again sitting meta to one another. Okay, but now I have a bit of a problem here because aniline, or rather this amine group with its benzylic lone pair, is what? So this one's orthopara. And what about my alkyl group? Also orthopara. Right? So how am I going to get this reaction where they're actually sitting meta to one another? Well, let's go back to the first of our two steps here. That nitro group that I put on is a meta director. All right, so as long as I don't reduce it before following it up with this reaction here, it would direct any incoming substituent to the meta position. So I'm going to first put on that nitro group. Let's actually draw this out step by step here so we can make sure to see how this is going to work. Let me move this one down here. First, I'm going to do the nitration step. This will create nitrobenzene. Second, I'm not going to reduce it yet. I'm going to attach that methyl group using that Friedel-Crafts reaction. I guess I can draw it in the same orientation to make it clear. Since that nitro group is a meta director, that methyl group will be directed to the meta position. And now I'm ready to do that last step, zinc, HCl. We actually got to follow it up with the NaOH in a different step. All right, but then when I do steps 3 and 4, that's how I'll get to my final product here. All right, so again, we sort of set aside and put a special little box around these 4 reactions that convert ortho-para to meta-directors, and now we see why that's very important to keep in mind in our synthesis steps here. Again, the order very much so matters for these reactions. Okay? So, last one here. There's something that immediately jumps out to me and gives me a clue about the type of reaction that I'm going to need to do. And what is that? That phenol, right? There's only one way that we know how to put these nucleophiles on a ring here, right? And that is that nucleophilic aromatic substitution reaction. And remember, we have these strict conditions for molecules that will undergo a nucleophilic aromatic substitution reaction. So this time, let's just take one step back from what this product is to what would have had to have come before it, would have had to have had that good leaving group in that position. Okay? Does this reactant right here undergo nucleophilic aromatic substitution? It needs those 2 conditions, right? I have a chloro group in the para position, right? That was one of our conditions. And then what about CBr3? This is one of those strong meta-directing, strong electron withdrawing groups. So along with the nitro group, this thing would be perfect for nucleophilic aromatic substitution. Okay, so I know here, I'm not sure how to get there yet, but I know that this last step will just be to add NaOH or add hydroxide to this product here. Okay, so then how do I get there? Let's again sort of think about how we could make these groups here. The chlorine's kind of the easy one. All right, but what about this tribromomethyl group here? Yeah, so we don't know how to do it in one move, but what we do know how to do is to first add the methyl group using one of those Friedel-Crafts reactions, and then we can turn around and do the excess of NBS. All right, so these 2 steps would create that group there. All right, so given that, take a second and see if you can't figure out what order we got to put these in order to actually get the product that we want here. So, after this NBS step, that tribromomethyl group is a meta-director, right? A strong electron withdrawing group. The alkyl group by itself would be ortho-para, and so would the chlorine. And since these are sitting ortho-para from one another, or sitting para more specifically from one another, I got to do one of those 2 reactions first. And it actually doesn't really matter the order in terms of getting your product. You could first do the CHBr or CHCl, AlCl3, and then do the chlorine. Or you could switch those up. Have the chloro come first, and then the methyl group. All right, and I'm not trying to be too crazy, so I would accept either of these. But let's think for a second, because practically speaking, one of these orders would actually be better than the other. All right, remember those halogens are sort of in a weird category here. Find my freaking million-page document cheat sheet. Okay. In that they are ortho-para-directors, but they're weak deactivators. My methyl group are ortho-para-director, but they're weak activators, right? Activating means it will react faster than benzene. Deactivating means it will react slower than benzene, right? So although either of these two would produce the same product, if I waited long enough, it would be way more efficient to do the reaction that's going to help speed the next step up than it would to do the reaction that's going to slow the next step down, right? So by putting the methyl group on there first, that will react even better than benzene, putting that chloro group on there. If I did the reverse, I'd put that chloro group on there, and it would direct the incoming methyl group to the right position. It would just take way longer, okay? So again, I would accept either of these because I'm not going to be too crazy about it. But one of these is more preferential than the other. All right. So now after this step here, after these two steps, oops. I will have my methyl group and my chloro group pair to one another. And yes, I would also have a mixture of the ortho product in there. We're kind of assuming that we're able to separate those out here to get our desired product. So now I just got to close this gap here between my methyl chloro group here and my tribromo methyl chloro derivative. And again, that would be with that excess of NBS. All right, so step 3, excess NBS. Step 4 would be to add that hydroxide ion in there, sodium hydroxide. All right, so obviously these problems are much more challenging. They're like little puzzles here, right? We got to take these pieces that we learned at the beginning, these separate reactions, and we got to stick them together in such a way that we actually get our desired product out of it. Cool. All right, our first